Space has always captured humanity's collective imagination. Among the pantheon of celestial bodies that have fascinated us, Jupiter stands out as the largest planet in our solar system. Its vibrant stripes and prominent great red spot make it easily recognizable. But there's far more to Jupiter than its size and famous storm, and our knowledge has grown exponentially with advancements in space technology and exploration. Jupiter is a gas giant consisting mostly of hydrogen and helium. Its diameter is approximately 11 times that of Earth, and it's so large that over 13 Earths could fit inside it. Despite its size, Jupiter has the shortest day of all the planets, rotating on its axis every 9.9 hours. Jupiter's magnetic field is the strongest of any planet in the solar system, created by electrical currents driven by its fast rotation and the movement of metallic hydrogen within its outer core. Jupiter's famous bands are actually high-pressure zones characterized by lighter-colored clouds. Conversely, its darker regions are low-pressure zones. The vibrant colors we see are due to different types of clouds. Ammonia crystals create the white bands, while other chemicals produce the reddish, brownish, and yellowish hues. As for the Great Red Spot, this iconic feature is a persistent high-pressure region in the atmosphere, resulting in a storm that's been ongoing for at least 300 years. The Great Red Spot is one of the most recognizable features of Jupiter, the largest planet in our solar system. At its widest point, it stretches 1.3 times the diameter of Earth, although its size varies over time. Notably, it has been shrinking in recent decades. The storm has been continuously observed since the late 19th century, but historical records suggest its existence for at least 300 years. The Great Red Spot is located in Jupiter's southern hemisphere, nestled within a westward-moving jet stream called the South Equatorial Belt. The red color of the Great Red Spot is still a subject of research. It's thought that the color may come from complex organic molecules, red phosphorus, or possibly compounds containing sulfur, though the exact chemical reactions that give the spot its vivid color remain a mystery. The storm rotates counterclockwise with a period of about 6 days. Interestingly, the rotation speed, size, and color of the spot can change, reflecting the storm's complex interaction with its surroundings. The longevity of the Great Red Spot is intriguing. While storms on Earth last for days or weeks at most, the Great Red Spot has persisted for centuries. This longevity is likely due to Jupiter's rapid rotation and lack of a solid surface, which minimizes frictional dissipation of the storm's energy. The Great Red Spot is a window into the atmospheric dynamics of Jupiter, a gas giant with conditions vastly different from our home planet. Understanding this celestial maelstrom not only unravels the secrets of Jupiter but also sheds light on the broader principles governing atmospheres, including our own. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who discovered them in 1610. Each of these moons is a world unto itself. Io is the most volcanically active body in the solar system, its surface covered in sulfur and sulfur dioxide, giving it a colorful, mottled appearance. Europa has a cracked surface, and scientists believe it might harbor a subsurface ocean, making it a potential site for extraterrestrial life. Ganymede, the largest moon in the solar system, is the only moon known to have its own magnetic field. Callisto, characterized by an extremely cratered surface, is also believed to have an ocean beneath its surface. Jupiter is known to have 79 moons, but additional moons may have been discovered since then. Saturn isn't the only planet with a ring system. Although much fainter and smaller, Jupiter also has rings composed mainly of dust particles from impacts on the planet's small innermost moons. These rings were first discovered by NASA's Voyager 1 spacecraft in 1979. The study of Jupiter has come a long way since Galileo's first observations. Multiple missions, such as Pioneer 10 and 11, Voyager 1 and 2, Galileo, Juno, and more, have been sent to Jupiter to study its composition, magnetic field, and moons. Pioneer 10 and 11 were the first spacecraft to make a close approach to Jupiter, providing valuable data about its radiation belts, magnetic field, and some moons. Voyager 1 and 2 made significant discoveries, such as detecting Jupiter's rings and confirming Io's volcanic activity. The Galileo orbiter spent 8 years studying the planet and its moons, and the attached probe made a direct plunge into Jupiter's atmosphere, providing the first direct measurements of its composition. The Juno mission, still ongoing as of 2021, has made significant contributions to our understanding of Jupiter's internal structure, atmosphere, and magnetosphere. Jupiter, the colossal gas giant, remains a focal point of curiosity for astronomers and space enthusiasts alike. Its impressive size, complex atmospheric dynamics, multitude of moons, and faint ring system make it a fascinating object of study. As we continue to explore Jupiter through telescopic observations and space missions, we unravel the secrets it holds, enriching our understanding of the cosmos. For now, we marvel at the celestial symphony Jupiter conducts, its presence a testament to the intricate, diverse, and vast nature of our solar system. Venus is nearly identical to Earth in size, making it one of our most similar neighbors in the solar system. With a mean radius of about 3,760 miles, it's approximately 95% the size of Earth, and its mass is about 81.5% that of Earth. This similarity in mass and size means that Venus also has a comparable density to Earth, approximately 5.24 grams per cubic centimeter, implying a similar rock-iron composition. Venus and Earth have a comparable structure, a central iron core surrounded by a rocky mantle and a thin crust. The core of Venus, while not as well understood as Earth's, is believed to be partially liquid, similar to Earth's. This iron core is estimated to be about 2,000 miles in diameter. Above the core lies Venus's mantle, composed of silicate rock that extends up to approximately 1,550 miles from the planet's center. This is overlaid by a thin crust estimated to be 6 to 12 miles thick. The rotation of Venus is a unique characteristic among the planets of our solar system. Unlike most other planets, which spin on their axis in the same direction that they orbit the Sun, Venus rotates in the opposite direction. This phenomenon isn't yet fully understood by scientists, but some believe it may be due to a massive collision with a celestial body in the past, which altered the planet's rotational dynamics. Venus rotates extremely slowly, with a sidereal day, a full rotation on its axis, taking 243 Earth days, the slowest rotation of any planet in the solar system. This slow rotation contributes to the planet's lack of a significant magnetic field. Another quirk of Venus's rotation is that a solar day on Venus, the time from one sunrise to the next, is shorter than its sidereal day. Due to its retrograde rotation and orbit around the Sun, the solar day on Venus is about 116.75 Earth days. The planet's year, the time it takes to orbit the Sun, is about 225 Earth days, which is shorter than its sidereal day. This makes Venus one of the few planets where a day is longer than a year. The surface gravity on Venus is about 90% of the surface gravity on Earth. This means that if you were able to stand on Venus, you would feel slightly lighter than on Earth. However, the extreme atmospheric pressure and temperature would make it impossible for humans to survive without protection. Venus's surface appears to be geologically young, with a relatively low number of craters, indicating a surface age between 300 million and 600 million years old. Scientists believe that Venus undergoes a cyclical process where heat from the planet's interior causes the surface to be repaved in a global resurfacing event. There is strong evidence of widespread volcanic activity on Venus, thousands of volcanoes dot its surface, ranging from less than a mile in diameter to over 150 miles. The planet has far more volcanoes than any other in our solar system. However, there is currently no definitive evidence that these volcanoes are still active. Although recent studies suggest that some may have erupted within the last few million years, Venus doesn't experience significant tectonic activity like Earth. While Venus does have mountain ranges and rift valleys similar to those seen in tectonically active regions on Earth, it lacks the kind of large, distinct tectonic plates seen on our home planet. This might be due to the planet's slow rotation, which limits the Coriolis effect necessary to drive large-scale tectonic activity. Venus's atmosphere is one of its most distinctive and intriguing characteristics. The atmosphere is primarily composed of carbon dioxide, with most of the remainder being nitrogen. However, there are also traces of other gases such as sulfur dioxide, water vapor, carbon monoxide, argon, and helium. This composition is vastly different from Earth's nitrogen-oxygen atmosphere, making Venus's air toxic to humans and most known forms of life. The atmosphere of Venus is arranged in several layers: the troposphere, extending from the surface to about 40 miles up, the mesosphere, stretching from the top of the troposphere to about 56 miles high, and the thermosphere, which reaches up to 125 miles above the planet's surface. Above this is a transitional region called the exosphere, which merges with the void of space. The high concentration of carbon dioxide in Venus's atmosphere creates a strong greenhouse effect, trapping heat and making it the hottest planet in the solar system, hotter even than Mercury, which is closer to the Sun. The greenhouse gases in the atmosphere absorb heat energy radiated from the Sun, preventing it from escaping back into space. This results in surface temperatures averaging around 467 degrees Celsius, hot enough to melt lead. There is very little temperature variation between day and night or between the equator and the poles, due to the thick atmosphere's efficient heat distribution. This results in a virtually constant furnace-like temperature all over the planet's surface. The atmospheric pressure on Venus is enormous, approximately 92 times greater than Earth's sea level. This is equivalent to the pressure experienced 0.62 miles deep in Earth's oceans. A human exposed to such pressure without protection would be crushed. Despite this, high up in Venus's atmosphere, approximately 31 miles above the surface, the pressure and temperature conditions are similar to those on Earth's surface. Venus's atmosphere is perpetually cloaked in thick, opaque clouds that cover the entire planet. These clouds reflect about 75% of the sunlight that reaches Venus back into space, which is why Venus is so bright and easily visible from Earth. The winds in Venus's upper atmosphere are incredibly fast, reaching speeds of up to 450 miles per hour, much faster than the strongest hurricane winds on Earth. These winds move in a phenomenon known as superrotation, where the atmosphere rotates much faster than the planet's surface. Near the surface, however, winds are much slower, typically less than a few miles per hour. Venus boasts the highest mountain in the solar system, Maxwell Montes, rising 20 kilometers above Venus's mean surface level. The planet's surface is also marked by numerous impact craters, extensive lava flows, and unique surface features like coronae, circular structures caused by the upwelling of hot material from the mantle, and arachnoids, circular structures with a complex pattern of fractures. Due to Venus's slow rotation and dense atmosphere, the planet doesn't experience significant seismic activity like Earth. However, recent studies suggest that Venus may still be geologically active. Venus has been a target of interest since the dawn of space exploration. The Soviet Union's Venera and Vega missions, NASA's Pioneer Venus, and the European Space Agency's Venus Express have all contributed significantly to our understanding of the planet. The Venera program achieved many firsts, including the first human-made device to enter the atmosphere of another planet and the first successful landing on another planet. These missions provided valuable data on Venus's atmosphere and surface. More recently, NASA's Magellan orbiter mapped almost the entire surface of Venus using radar to penetrate the thick cloud cover. This mission revealed details about Venus's surface features and geology. Despite the challenges posed by Venus's harsh conditions, scientists are interested in further exploring the planet. NASA's planned Veritas and Da Vinci Plus missions aim to study Venus's geologic history and atmospheric conditions, providing insights into whether Venus might have once harbored liquid water or even life. Meanwhile, the European Space Agency's Envision mission will focus on understanding why Venus and Earth took such different evolutionary paths. Japan's Akatsuki mission is currently studying Venus's atmosphere and weather patterns. Venus, our neighboring planet, is an intriguing world of extremes. Its harsh environment poses significant challenges to exploration, yet its similarity to Earth in size and composition, along with hints of potential past water and geologic activity, keep our curiosity alive. As we prepare for new missions to Venus, we stand on the brink of major discoveries that could reshape our understanding of the solar system and our place in it. Venus serves as both a warning and an opportunity for scientific discovery, offering reflections on our own planet's potential future. Our solar system is a harsh environment, and volcanoes are destructive everywhere, from the ice volcanoes of Saturn's moon Enceladus to the immense lava fields of Jupiter's moon Io, to our own planet Earth. It is true that we would not be here without volcanoes. They influence and alter our climate. Volcanoes are both creators and destroyers of existence. Today's spacecraft and observatories have revealed volcanoes on planets we once believed to be dead. The discovery of volcanoes on an object smaller than the Moon was a major surprise. If there are volcanoes on other worlds, could there also be life? Volcanoes are among the most potent natural occurrences on Earth. They create new land and destroy the old, emitting gases that alter the atmosphere. Deep in our oceans, volcanic heat fuels bizarre new forms of life. Volcanoes help sustain life on Earth. Now, we look for signs of life on other planets, knowing that life requires water and energy. This is where volcanoes come in, as they generate tremendous quantities of energy. If we locate volcanoes on other planets, we may discover life. The search begins with Venus, the planet that orbits closest to Earth. Venus and Earth have similar masses. Around 3 billion years ago, both planets had new land, new oceans, and atmospheres conducive to life. However, something went wrong on Venus, causing its history to diverge drastically from Earth's. Venus took a definite turn to the dark side a long time ago, and today it is Hell, our malevolent twin planet. The surface of Venus is like a furnace, with temperatures reaching 900 degrees Fahrenheit, hot enough to melt some metals. Venus is a greenhouse world, its atmosphere containing a high concentration of carbon dioxide, which traps solar heat like a blanket. Actual images of Venus's surface reveal a desolate, extremely hot wasteland. The planet was annihilated by its dense CO2 atmosphere, which was produced by volcanoes. Spacecraft in orbit provided the initial clues, as radar broke through Venus's thick clouds, revealing volcanic formations all over the planet. These formations resemble Earth's shield volcanoes, round and flat, with slow, long-lasting eruptions. Once we mapped the entire surface of Venus using cloud-penetrating radar, we discovered that many of its landforms were quite familiar, particularly enormous shield volcanoes that resemble those in Hawaii. The radar images of Venus were identical to those of Hawaii's shield volcanoes. In the past, Venus was home to volcanoes. We were astounded to see a picture of Venus for the first time and discovered a cratered volcanic surface. There are at least 1,000 large volcanoes and possibly tens or hundreds of thousands of smaller ones. Lava plains cover 3/4 of Venus's surface, evidence of an ancient catastrophe. This could have been a home for life, but instead, it was consumed by flames. Venus's volcanoes expelled trillions of tons of carbon dioxide into the planet's atmosphere, causing the temperature to rise dramatically and evaporating the oceans. On Earth, carbon dioxide is absorbed by rocks and oceans. However, on Venus, with no water and extreme temperatures, carbon dioxide cannot combine with minerals. Over time, as fewer methods existed to remove CO2 from the atmosphere, Venus's volcanoes effectively sanitized the entire planet. If Venus ever supported life, that potential was destroyed. While Earth is the only known planet with life, this could change. Jupiter, with its moons once believed to be frozen and lifeless, presents a mystery. On Venus, volcanoes transformed a planet similar to Earth into a hyperheated inferno. While volcanoes on a planet like Earth are not surprising, the discovery of volcanoes on the Moon was astonishing. In March 1979, the Voyager 1 spacecraft astonished us by providing the first close-up images of Jupiter's tiny moon, Io, a world we once believed to be frozen and lifeless. But then something strange was observed. They noticed an arc near the moon, almost as if there was a second moon behind it. Everyone was puzzled and asked, what could that be? Io is supposed to be lifeless, dull, and uninteresting. But soon people realized, oh my God, it's a volcanic eruption. We discovered that Io is covered in volcanoes and is geologically extremely active, with constant volcanic eruptions. These eruptions release vast amounts of sulfur, which gets intensely heated. Sulfur changes color as it heats, going from red to orange, yellow, or even black. This gives Io a striking appearance, with images resembling a pizza with different types of cheese and black spots representing the small dark regions on its surface. Io is not dead, it's alive and evolving, with over 400 active volcanoes. The largest eruption, called Poly, shoots lava from a massive lava lake, and the plume extends about 400 kilometers into space. If we could stand by the edge of that lava lake, watching the plume shoot into space, it would be a spectacular sight. The eruptions on Io are so massive that, because the moon is so small, there's nothing to hold the lava back, there's almost no atmosphere and very little gravity. These colossal eruptions make Earth's volcanoes look like mere fireworks. How can such a small moon be so volcanic? The answer is Jupiter. Similar to how Earth's moon causes tides in our oceans, Jupiter creates rock tides on Io. Io's orbit around Jupiter isn't perfectly circular. Sometimes it's closer, sometimes farther away. Jupiter's gravity pulls on Io, stretching and squeezing it during every 2-day orbit. This gravitational tug makes Io's surface rise and fall by nearly 300 feet, creating tremendous heat and pressure. Wherever there are weak points in the crust, lava erupts. Unlike Earth, where volcanic activity is localized along tectonic plates or in weak spots, on Io, the entire moon is an active volcanic hotspot. Io is the most volcanically active body in the solar system, driven by the immense power of Jupiter's gravity. This taught us something new: internal energy sources, driven by forces like gravity, can power volcanism differently than they do on Earth. Io is a world of lava, extremely hot and violent. It's hard to imagine anything surviving there. While we found strange eruptions on many planets and moons, Earth is still the only world where volcanoes are tied to life, or so we thought. This is Europa, another moon orbiting Jupiter. Nearly 500 million miles away from the Sun. Europa is a sphere of ice, about 2,000 miles wide. From afar, its surface appears polished, but up close, it tells a different story. Like its neighbor Io, Europa is pummeled by Jupiter's massive gravity. Its surface rises, twists, and forms ridges and deep cracks. When we first saw close-up images of Europa, they looked strangely familiar, resembling Arctic ice flows. And it turns out they are quite similar. Beneath Europa's several-mile-thick icy crust lies a global ocean. Magnetic measurements suggest that Europa's ocean is an incredible 60 miles deep. The gravitational force of Jupiter heats Europa's rocky interior, melting the ice above. As the core is stretched by tidal forces, it heats up, and it's possible that there's a boundary where the heat from the core meets the liquid water of the ocean. On Earth, underwater volcanic eruptions teem with life. Could the same be happening on Europa? In the darkness, with crushing pressures up to 2,000 times greater than those on Earth, life might find a way to survive. It's a harsh environment, but perhaps a cradle for life. If life exists in the extreme conditions on Earth, in boiling heat, crushing pressure, and total darkness, why not on Europa? Europa has energy sources, volcanic activity, liquid water, and complex hydrocarbon chemistry, all ingredients that could support life. While life would be difficult on Europa, it's not impossible. There is life on Earth in every extreme condition, including searing heat, crushing pressure, and absolute darkness. Life on Europa may resemble life on Earth in unexpected ways. If life exists beneath Europa's ice, it would likely be aquatic, but without eyes due to the lack of significant light. These organisms would probably feed off the energy from volcanoes and would use sonar to navigate their surroundings. Volcanoes on Europa could be the birthplace of new life. It's even possible that Europa is typical and that this is the norm for planets with life, while Earth might be the exception. Europa could serve as a model for the billions of moons in the universe that have liquid oceans. Our understanding of potential habitats for life has suddenly expanded several billion times by looking at Jupiter's moons. Our solar system alone has more than 170 moons. Multiply this by the size of the universe, and that's a vast number of potential places for life to exist. All that's needed is liquid water and a source of energy, which volcanoes can provide, and these are common throughout the universe. This brings us to Saturn, which is twice as far from the Sun as Jupiter, yet it too has volcanic moons that could potentially support life. Saturn is one of the more unusual planets in our solar system, with a 600,000-mile wide ring system and an astounding 62 moons, one of which holds a secret. Enceladus is one of Saturn's smaller and more distant moons, long known for its ice-covered surface, which is extremely bright and reflective. However, when the Cassini spacecraft visited Saturn, it made a remarkable discovery, not on Saturn itself, but on one of its moons. Cassini revealed a massive plume erupting from Enceladus, backlit by the Sun, providing conclusive evidence of volcanic activity. The spacecraft zoomed in on the moon's south pole to capture enormous craters scarring its surface. At Enceladus's south pole, large fissures open and close as the moon orbits Saturn, driven by tidal forces. These fissures stretch for hundreds of kilometers, and as they open, they move at speeds of about 100 miles per hour. It would be an incredible sight. The immense gravitational forces cause the surface to expand and contract with great speed, producing enough heat to melt ice and form oceans beneath the surface. The conditions in Enceladus's subsurface ocean seem ideal for life. The water is at a favorable temperature, much like seawater on Earth. The chemistry of the water, observed as it erupts from the fissures, indicates it contains salt and organic matter, suggesting a strong possibility of life within this mysterious moon. Cassini has also detected complex carbon molecules in the ice particles, adding further evidence that life could exist deep within Enceladus. And Enceladus might not be the only moon of Saturn with potential for life. Titan, one of the largest moons in the solar system, also holds promise. It is the only moon with a thick atmosphere. Though Titan is a frozen world with ice as hard as rock and lakes of liquid methane, we might find evidence of volcanoes and the tantalizing possibility of extraterrestrial life. Volcanoes are among the most destructive forces in the universe, as seen on Io's volcanic inferno and Triton's icy nitrogen explosions. Even on Saturn's enigmatic moon Titan, volcanoes could offer the prospect of life. Titan, with a diameter of 3,000 miles, is larger than Mercury and has the thickest atmosphere of any moon in the solar system. Titan has weather patterns, cyclones, wind, rain, and lakes, but with temperatures so low that liquid methane takes the place of water. The atmosphere is filled with compounds essential for life. Titan has proven to be one of the most intriguing places in the solar system. It's an active world with a dense atmosphere, similar to Earth's, thanks to the presence of nitrogen. Organic molecules high in Titan's atmosphere suggest methane gas interacts with sunlight to produce compounds vital for life. But if sunlight continuously converts methane into organic compounds, why doesn't the methane run out? Methane is abundant in Titan's atmosphere, but it's quickly depleted by sunlight, so there must be a source replenishing it. Scientists believe the source of this methane may be volcanic activity. Cassini spotted what appears to be a crater on Titan, surrounded by different materials visible in infrared images. The green areas around the crater could indicate volcanic plains where lava, likely a mixture of ammonia or water, erupts from Titan's interior. The methane and ethane released by Titan's volcanoes may also contribute to its thick cloud cover and orange atmosphere. This atmosphere likely originated from volcanic outgassing. Even on a rigid world like Titan, volcanoes need heat, which is provided by two sources: radioactive decay inside the Moon and Saturn's immense gravitational pull. These forces generate enough heat to turn ice into water and liquid methane into gas. Could Titan's volcanoes give life a chance to survive? The chemical reactions necessary for life, as we know it, require an atmosphere, a solid surface, liquid water, and heat. Volcanoes could provide all of these on Titan. If life exists on Titan, it would be truly alien, possibly breathing hydrogen instead of oxygen and swimming through methane reservoirs at 300 degrees below zero. There could be oceans of ethane, as well as tidal pools, volcanic, and hydrothermal activity. Perhaps volcanic heat could provide enough energy to support life on Titan. This is speculation, but it can't be ruled out. However, we might not need to travel so far to discover signs of life. We may find it on Mars, a volcanically active world much closer to home. Volcanoes are everywhere in the solar system. Planets like Io, Titan, and Triton are intricate, volatile, and violent. Once, we believed that Earth was the only planet with both volcanoes and life. Now, we find volcanoes all over, but alien life has yet to be discovered. Volcanoes represent the raw power of creation and destruction, hand in hand. Without volcanoes, life as we know it on Earth wouldn't exist. Volcanic cauldrons are the birthplace of life, creating new landscapes, seeding the atmosphere with complex chemicals, and replacing the old with the new. If volcanoes are linked to the processes of life, where is life on other planets? The answer might lie in ancient times when the solar system was young, on a planet similar to our own. This is Mars. 3 billion years ago, volcanoes were active, and the greatest volcano in the solar system still stands. The cliffs leading up to it are more than 6 miles high, so high that even Mount Everest would seem small in their shadow. This is the formidable Olympus Mons. Covering an area the size of Arizona, Olympus Mons has a crater that is 53 miles wide. A structure this large takes millions of years to form, a time frame that volcanoes on Earth, with its moving tectonic plates, never have. On Earth, tectonic plates are constantly in motion. In Earth's depths, a stationary hotspot forces magma to the surface, creating new volcanic islands. But while the hotspot remains in place, the surface moves, and new islands form over time. Mars is different. Its crust is solid and immobile, with no tectonic activity. So, if there is a hotspot, it remains in one place, allowing volcanoes to grow larger and larger. This is why Olympus Mons is so enormous. Today, Olympus Mons is a frozen relic of a once warmer Mars. Though an extinct volcano, it stands as a giant on a planet with a thin atmosphere. However, the ancient volcanic landscapes of Mars could one day support life. Evidence on Earth shows that volcanoes, like those in Hawaii, create mysterious tunnels known as lava tubes. These form when rivers of molten rock flow beneath the surface and cool, leaving behind a solid crust. Lava tunnels are created when basaltic lava at 2000 degrees Fahrenheit forms a crust, with the molten river continuing to flow underneath, creating caves. Recent images suggest that Mars's volcanoes may have also formed lava tubes. Any rocky planet with basaltic volcanism likely has lava tunnels. After millions of years of volcanic inactivity, these lava tubes on Mars could become habitats for future life. They could even be used by humans. One of the major challenges future Mars settlers will face is radiation. Without protection, solar storms and cosmic rays could be deadly. The tunnels and caverns of Mars's extinct volcanoes could provide shelter, holding air and protecting inhabitants from harmful radiation. A long-dead volcano could one day help Mars become a new cradle for life. Volcanoes have the power to destroy and create. A supernova, the largest eruption ever observed by humans, is an even greater example of this duality. A supernova is the incredibly bright and powerful explosion of a dying star. One type of supernova occurs when a massive star, at least 5 times the size of the Sun, explodes in a final burst. Massive stars consume vast amounts of nuclear fuel in their cores, generating immense amounts of energy. This energy creates heat, which in turn creates pressure. The pressure from nuclear combustion within a star counteracts the force of gravity, which tries to compress the star. A star maintains equilibrium between 2 opposing forces, gravity pulling inward and the pressure from nuclear fusion pushing outward. As the star burns through its fuel, it cools down, causing the pressure to decrease. Eventually, gravity wins, and the star collapses rapidly. Imagine an object with a mass 1,000,000 times that of Earth collapsing in just 15 seconds. The collapse happens so rapidly that it generates immense shock waves, causing the star's outer layers to erupt. Typically, what remains is a dense core and an expanding cloud of hot gas, known as a nebula. A supernova of a star that is about 10 times the size of our Sun or more may leave behind black holes, the densest objects in the universe. Imagine being an astronomer in the early 17th century, before the invention of the telescope, exploring the universe with your limited vision. Then, one day, you witness a truly spectacular sight. Over the next several weeks, a new star shines brighter than Venus. Its brightness is so intense that it's visible during the daytime. As months pass, the brightness fades slowly but remains visible. Skywatchers across Europe, the Middle East, and Asia saw the same phenomenon that German astronomer Johannes Kepler observed in 1604. We now know this event was not a new star, but a supernova, a massive explosion of a star at the end of its life. The last supernova observed in the Milky Way occurred in 1604. There may have been other supernovas since then, but they've been hidden by interstellar gas and dust, making them difficult to detect. The Crab Nebula is the remnant of a supernova that occurred thousands of years ago, with its light reaching Earth around 1054. The supernova discovered in the Large Magellanic Cloud in 1987 was the closest supernova event to Kepler's since then. Several supernovas in other galaxies have also been documented, visible only with telescopes, which Kepler's contemporaries would have missed entirely. It has been 418 years since we last witnessed a star explode in our galaxy. A nearby, bright supernova is long overdue. Scientists predict that 1 to 3 stars should explode in our galaxy per century. When the next supernova occurs, modern astronomers will be far better prepared than Kepler or even scientists from a few decades ago. Today, astronomers have access to telescopes capable of capturing visible light, and when used together, they can simulate what it would be like to fly close to a supernova and observe it with our own eyes. In addition, we now have telescopes sensitive to infrared light, which has longer wavelengths than visible light and can penetrate gas and dust more effectively. This allows us to observe objects that would otherwise be hidden. Instruments like the James Webb Space Telescope, which primarily records in infrared, have expanded our view. The electromagnetic spectrum includes both visible and infrared light, but supernovas also emit neutrinos, subatomic particles that can now be detected with modern instruments. These detectors can also record gravitational waves, tiny ripples in spacetime thought to be released by exploding stars. 2 types of supernovas have been identified. A Type 1 supernova occurs when a white dwarf star pulls material from a companion star until a runaway nuclear reaction blows it apart, sending debris hurtling into space. In a Type 2 supernova, a star runs out of nuclear fuel and collapses under its own gravity, which triggers an explosion. Both types of supernovas can be brighter than their entire host galaxy. Type 2 supernovas are particularly interesting because they emit a large number of neutrinos alongside light. In fact, neutrinos can begin to be emitted before the explosion itself. When a supernova occurred in 1987, neutrino research was still in its infancy, but 3 detectors managed to capture 24 neutrinos. If a supernova occurs in our galaxy now, we could expect hundreds, if not thousands, of neutrinos to be recorded by the global network of detectors. Fascinating signals might be produced if a collapsing star forms a black hole, preventing the star from ejecting any further debris. In such cases, the neutrino emissions would suddenly stop, a clear indication that a black hole has formed. Astronomers could then use databases of stars to locate the missing star and confirm the formation of a black hole. Detecting gravitational waves from a supernova in our galaxy would complete the scientific hat trick. Gravitational waves, predicted by Einstein, are distortions in spacetime caused by the acceleration of massive objects. These waves were first detected in 2015 and have so far been attributed to mergers of black holes and neutron stars. A supernova in our galaxy should also produce such signals. Astronomers have used computer models to study supernova explosions for decades, but many details remain unknown. Data from gravitational wave studies may help solve some of these mysteries. Could a nearby supernova pose a danger to life on Earth? In theory, yes, but it would need to be relatively close. Fortunately, no stars near Earth are currently at risk of exploding. A close supernova would release harmful ultraviolet, X-ray, and gamma radiation into space for weeks, potentially damaging Earth's protective ozone layer. Even if the radiation didn't reach the ground, without the ozone layer, the sun's lethal UV radiation would flood the planet, killing everything from phytoplankton in the oceans to humans. It's possible that something like this occurred in Earth's past, around 360 million years ago, near the end of the Devonian period, when a massive extinction event may have been caused by a supernova. On the other hand, supernovas aren't just destructive forces, they can also give rise to new life. Astronomers and physicists explain that the nuclear processes happening deep within exploding stars, which are spread throughout space by the blast waves they create, are the source of many of the heavy elements humans depend on. In this way, a supernova could be considered the gold standard for astronomers. On a night in early September 1859, people across America witnessed a blood-red aurora so bright that miners in the Rockies emerging from their tunnels thought it was sunrise. The light was intense enough that, even at midnight, people could read newspapers. This spectacle wasn't limited to the U.S., it was visible across the world. At the time, no one knew why it happened. However, earlier that day, an astronomer had observed something on the sun's surface, which he called a white light flare. Back then, the flare and the aurora seemed unrelated, but today we know that the magnificent aurora was caused by that flare, which was, in fact, a coronal mass ejection. If such a violent event occurred today, it could devastate our modern technological world. The sun is the most familiar object in the sky. It provides all life on Earth with heat and light. It's so massive that it's difficult to imagine, comprising 99% of the solar system's total mass. This nearly perfect sphere has a diameter of 1.4 million kilometers and has been powered by hydrogen and helium fusion for the last 5 billion years. Yet, from an astronomical perspective, it's an ordinary G-type main sequence star, also known as a yellow dwarf. However, appearances can be deceiving. The sun frequently emits solar flares and explosions of plasma particles and radiation that travel deep into space, a process known as the solar wind. Solar storms, however, are much more violent eruptions. The most dangerous type is the coronal mass ejection, which has the potential to bring our high-tech society to its knees. Today, we'll explore just how catastrophic a coronal mass ejection could be and what astronomers are doing to monitor the sun to predict when these events might occur. Step back in time to 1859. In Victorian Britain, it was perfectly acceptable for a gentleman to take an interest in solar astronomy, and one man, Richard Christopher Carrington, did so with great success. While no portraits of him survive, Carrington made many important discoveries. He observed that different latitudes of the Sun rotated at slightly different speeds, indicating that the Sun wasn't a solid body but a fluid one. He also realized that sunspots could signal the onset of a solar storm. On Thursday, September 1, 1859, there were no clouds in the sky, and Carrington, as usual, was observing sunspots. He used his telescope to project an image of the Sun onto a screen. At 11:18 a.m., he witnessed two brilliant beads of blinding white light appear in what he described as a kind of conflagration. Even more strangely, they vanished after just 5 minutes for no apparent reason. Carrington had just witnessed a coronal mass ejection, a massive magnetic explosion where a giant cloud of charged particles is hurled from the Sun's surface. 18 hours later, Earth was struck by an electromagnetic storm, later named the Carrington event. While the beautiful aurora lit up the skies across the world, a few telegraph systems went haywire due to power surges, but the event didn't significantly affect daily life. Keep in mind, though, that this was 20 years before the invention of the light bulb. That was in the past, but today the effects would be very different. Coronal mass ejections are relatively common, but they vary in size and direction. The question now is, what are the chances that something like the Carrington event could happen today, and how would it affect us? What exactly is happening on the surface of the Sun when we talk about solar wind and space weather? The Sun is made of magnetic fluid, and as that fluid rotates, it twists and distorts the magnetic field. A twisted magnetic field stores energy, which can lead to eruptions known as coronal mass ejections. These explosions are massive, sending 1 billion tons of material out at 1 million miles per hour. We want to know where these ejections are headed because if they move toward Earth, they could affect the technologies we rely on. A well-known incident occurred in Quebec in 1989 when power systems were disrupted for several hours. And as we've heard about the Carrington event from the 1800s, we wonder, what would happen if it occurred today? How would it impact us? Consider the technology we depend on now, GPS satellites that help us navigate, communication satellites, weather satellites, and even systems linked to the stock market. We also have larger power grids and extensive wireless technologies. We don't fully understand how all of this would respond to a solar event of that magnitude. How likely is it that a Carrington-like event could happen again? We know the Sun is still capable of producing such events. In 2012, there was a solar event that, fortunately, didn't head toward Earth, but it did pass by one of the spacecraft we use to monitor the solar wind. The event pushed the sensors on that spacecraft to their limits, and based on what we learned, we believe it was at least as powerful as the Carrington event, if not stronger. It was pure luck that the CME wasn't directed at Earth. How well can we predict such solar events? Can we forecast what the Sun will do a week, a month, or even a year from now? Once we detect a CME, we can start making predictions about its size, speed, and, most importantly, where it's heading. All of this can sound quite alarming. Space weather is a real concern, and the UK government recognizes this. The National Risk Register lists space weather as a threat on par with a flu pandemic. Engineers designing spacecraft are working to understand the most extreme conditions in space so they can build technology capable of withstanding them. Both NASA and the European Space Agency are preparing to launch satellites that will get closer to the Sun than ever before. The Met Office's Space Weather Operations Center, opened in 2014, is one of only 3 places in the world that can monitor the Sun's effects on Earth 24/7. Currently, the Sun has very few sunspots, and the side facing Earth isn't expected to produce any significant sunspots or coronal mass ejections. For now, things look calm, and spacecraft, satellites, and power supplies should remain safe for the foreseeable future. The problem is that our space weather forecasts only extend a few days ahead. We still don't know much about coronal mass ejections, such as their size, direction, or timing. In the near future, 2 new solar probes will get closer to the Sun than any spacecraft has before. NASA's Parker Solar Probe is set to fly close to the Sun's surface and pass through the source of its most energetic solar particles. This mission will measure the gas and magnetic field near the Sun to understand why solar material spreads into the rest of the solar system. ESA's solar orbiter is also expected to provide valuable insights by observing how sunspots, solar flares, and coronal mass ejections are linked to the solar wind. The success of these missions will be crucial for advancing our understanding of the Sun. We believe that the Sun's magnetic field is generated in a way similar to Earth's, but it is much more dynamic and changes constantly. Additionally, the Sun goes through an 11-year sunspot cycle, during which its magnetic fields move toward the poles and switch polarity. On top of that, the magnetic field extends into the solar system and affects all the planets. Solar Orbiter will measure these magnetic fields for the first time and give us the opportunity to observe how they move toward the Sun's poles. To accomplish this, Solar Orbiter will take images of the Sun's atmosphere and measure the number, speed, and temperature of the particles traveling through space between the Sun and Earth. The magnetometer, designed to detect the small magnetic fields carried by the solar wind, could be one of the most important and sensitive instruments. The Sun is a constant in our lives. It provides light, warmth, and even life itself. For Richard Carrington, who first recorded a coronal mass ejection, it was just a strange event. But now, we understand that these occurrences can cause significant damage to our world. With new satellites and more observations, we may be able to learn more about these events and predict when the next coronal mass ejection will happen. The universe is full of strange and surreal paradoxes that challenge our understanding, from the mysteries of quantum mechanics to the mind-bending properties of black holes. The universe presents us with numerous phenomena that defy our intuition and challenge our perception of reality. This video allows you to explore many things we do not yet understand about the universe, as well as paradoxes in what we think we know. Everything we know represents just 5% of the universe. What is the rest? Ordinary matter, protons, neutrons, and electrons, makes up only 5% of the universe. Staggeringly, the other 95% consists of something we cannot see, understand, or fathom. We refer to it as dark matter, which accounts for 27% of the universe, and dark energy, which makes up 68%. But what are these mysterious components of the universe? Dark matter and dark energy are two puzzling concepts in astrophysics that scientists use to explain strange observations about the universe. Dark matter is a type of matter that does not interact with light or any other form of electromagnetic radiation, meaning it cannot be directly detected by telescopes or instruments that rely on light. However, scientists infer its existence by observing its gravitational effects on visible matter, such as stars and galaxies. Dark matter is thought to account for around 85% of the universe's total matter, but we still don't know what it is made of. It doesn't behave like any of the known particles that make up ordinary matter, such as protons and electrons. Some theories suggest that dark matter consists of undiscovered particles that don't interact with light or radiation, while others propose it may be composed of exotic objects like black holes. Dark energy, on the other hand, is a hypothetical form of energy thought to permeate all of space, responsible for the universe's accelerating expansion. Unlike dark matter, which has a gravitational effect that slows down the universe's expansion, dark energy has a repulsive effect, speeding up the expansion. The exact nature of dark energy remains unclear, but it's believed to be a property of space itself, rather than a type of matter or energy we can directly observe. Scientists estimate that dark energy makes up about 68% of the universe's total energy. How many dimensions does the universe have? According to our current understanding, the universe has 3 spatial dimensions: length, width, and height, and 1 dimension of time, totaling 4 dimensions in spacetime. This is known as 4-dimensional spacetime. However, some theories in physics, such as string theory, propose that there may be more than 4 dimensions, potentially up to 11. These extra dimensions are believed to be curled up or compactified and too small to observe at our scale, meaning that although they may exist, they are not directly observable, and their effects on four-dimensional spacetime can only be inferred through their influence on physical phenomena that we can observe. These additional dimensions could help us unify the mathematical foundations of the four fundamental forces of nature: the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. Do these higher dimensions exist? And if they do, is there a way for us to measure their presence, or will we forever be trapped in our four-dimensional world? What if our universe is just one of many out there? The idea that our universe is just one of many universes, known as the multiverse theory, is a popular concept in modern cosmology and physics. According to this theory, there may be many other universes existing alongside our own, each with its own unique properties and laws of physics. If this is the case, it would have profound implications for our understanding of the universe and our place in it. For example, it could help explain why our universe appears to be finely tuned to support life, known as the anthropic principle. If there are countless other universes with different physical laws and properties, it would increase the chances of at least one of them being able to support life. The multiverse theory also raises questions about the nature of reality and how we define what is real. If there are many different universes with different physical laws, are they all equally real, or is our universe the only real one? What is time? Time is one of the most difficult properties of our universe to understand. Researchers say that time is a measurable period, a continuum that lacks spatial dimensions. There seems to be an obvious direction or flow of time, and it appears that we cannot travel backward in time. Why is this? Are we trapped in the arrow of time, perpetually moving forward? Is the passing of time intertwined with the way our universe works? According to the Big Bang Theory, time itself began with the rest of the universe around 13.8 billion years ago. Does that mean it makes no sense to ask what was before? Time is a fundamental concept in physics, often defined as the progression of events from the past through the present and into the future. It is a fundamental dimension in which events occur and is often represented as a continuous line or axis. In the context of physics, time is typically measured in units such as seconds, minutes, hours, and years. It is also an essential component of the space-time continuum, which is the four-dimensional fabric of the universe, consisting of 3 spatial dimensions and 1 temporal dimension. The flow of time is often described as unidirectional, meaning it moves forward and cannot be reversed. This is known as the arrow of time and is often associated with the second law of thermodynamics, which states that entropy, the measure of disorder or randomness in a closed system, tends to increase over time. The nature of time is still a subject of ongoing research and debate in physics and philosophy. Some theories propose that time is an emergent property that arises from the complex interactions of the universe's fundamental components, while others suggest that time is a fundamental property of the universe, like space and matter. Particles violating the laws of nature? In certain situations, 2 particles can seem to have an instant connection with each other, even if they are located at opposite ends of the universe. This phenomenon is known as quantum entanglement, where 2 particles become correlated in such a way that the state of one particle is instantly linked to the state of the other, regardless of the distance between them. While this may seem like a violation of the laws of nature, it is actually consistent with the principles of quantum mechanics. However, it is important to note that this does not allow for faster-than-light communication or a violation of causality. This is because, while the state of the entangled particles may be instantaneously correlated, there is no way to control or manipulate this correlation to transmit information faster than the speed of light. In fact, a fundamental principle in quantum mechanics, known as the no-communication theorem, states that it is impossible to use entanglement to transmit information faster than light. So, while quantum entanglement may seem like a strange and mysterious phenomenon, it does not allow for the violation of the laws of nature or the principles of causality. Could this feature of quantum mechanics one day allow us to send information instantaneously over large distances? Are we alone in the universe? There are at least 2 trillion galaxies in the observable universe, with more stars and planets in them than all the grains of sand on planet Earth. So, where is everyone? Why haven't we encountered life from elsewhere? Is life incredibly rare, or does it have a limited lifespan, destroying itself before it has the chance to seek out other life forms? What does this tell us about the future of humankind? The question of whether or not we are alone in the universe is one of the most intriguing and profound questions we can ask. Given the vast size and age of the universe, it seems unlikely that Earth is the only planet with the conditions necessary for life to emerge. There are likely billions of potentially habitable planets in our galaxy alone. However, the fact that we have not yet encountered any definitive evidence of extraterrestrial life is known as the Fermi paradox. There are many potential explanations for the Fermi paradox, including the possibility that life is indeed rare, but it is difficult for life to evolve beyond a certain point, or that intelligent civilizations have a limited lifespan and self-destruct before they can explore the galaxy. It is also possible that we simply have not looked in the right places yet. Our current methods of searching for extraterrestrial life are still relatively limited, and it is possible that more advanced techniques in the future could uncover evidence of life elsewhere in the universe. Does the self-reference problem distort our perception of the universe? We humans are also part of the universe we inhabit, so when we look out to study the stars and galaxies, are we really neutral observers of the universe? When we explore the universe, we are both observers and the subject of observation. How can we pretend to be neutral when we are deeply embedded in what we explore? Could it be that this self-reference problem affects the way we look at the universe and gives us an overwhelmingly wrong impression? The self-reference problem is indeed a complex issue when it comes to our study and perception of the universe. We are not neutral observers of the universe, but rather we are embedded within it. This self-reference problem can lead to potential distortions in our perception of the universe, as we may unwittingly project our own preconceptions and assumptions onto our observations. For example, we may tend to focus on phenomena that we find particularly interesting or relevant to our own existence, rather than taking a more objective and comprehensive approach. By acknowledging our own biases and limitations, we can work to develop more rigorous and objective methods of observation and analysis. Why is the universe seemingly so perfect for us? The universe seems to be perfectly made for us, but why is this? Why do the fundamental constants of our universe, such as the speed of light, have the values that they do, allowing life to exist? Could it be that there are infinite universes with infinite possibilities, and we merely happen to live in one that is perfect for life? There are a few possible explanations for this apparent fine-tuning of the universe. One possibility is the anthropic principle, which states that the universe is the way it is because it must be compatible with the existence of observers. In other words, the universe appears fine-tuned for us because if it were not, we would not be here to observe it. This is sometimes referred to as the selection effect. Why is it easier to destroy something than to put it back together? Entropy is the amount of disorder, chaos, or randomness in a system. One can never reduce entropy. Everything in the universe slowly moves towards disorder. It's very easy to smash a window, but impossible to put it back together exactly as it was before. The principle of entropy moves the universe from structure to chaos, from an ordered state to disorder. What does this tell us about the fate of the universe? As the universe continues to expand, it will eventually reach a state of maximum entropy, where all matter is uniformly distributed, and there is no energy gradient available to drive further processes. This state is known as the heat death of the universe, where the universe will be cold, dark, and lifeless. The universe is not a closed system, as it receives energy from stars and other sources, but the overall trend is towards increasing disorder and chaos. However, it is important to note that this process will occur over an extremely long time scale, likely trillions of years in the future. Can anything escape a black hole? We have observed the effects of black holes, and we have even seen one directly. The gravitational force of these massive objects pulls everything towards them, even light itself. What happens in the mysterious, infinitely dense center of a black hole? Could there exist such things as white holes, the opposites of black holes, that spew matter and time into our universe? According to our current understanding of physics, nothing can escape a black hole once it has passed the event horizon, which is the point of no return. The gravitational pull of a black hole is so strong that it warps space and time, and anything that crosses the event horizon is inevitably pulled towards the singularity at the center of the black hole, where the laws of physics as we know them break down. We do not know what happens at the center of a black hole, as our current understanding of physics is unable to describe the conditions there. It is commonly believed that the matter at the singularity is infinitely dense and compressed to a point of zero volume, known as a singularity. As for the possibility of white holes, which are hypothetical objects that are the opposite of black holes, there is currently no direct evidence to suggest that they exist. White holes are believed to exist at the other end of a hypothetical wormhole, which is a tunnel-like connection between 2 points in spacetime. However, there is no direct evidence to suggest that wormholes exist either. The universe is full of strange and surreal paradoxes. Our quest for understanding these is only just beginning. As we continue to push the boundaries of our knowledge and explore the furthest reaches of space and time, we can be sure that the universe will continue to surprise and challenge us in new and unexpected ways, spurring us on to new heights of discovery and understanding. We used to only know about the planets that circled around our sun, but now we know that there are rocky worlds and huge gas clouds that circle other stars. They have a great story to tell. The early history of these planets would have been very, very violent. Planets are made the same way everywhere. They come from the dust and other materials left over after stars are born. So, if they're all made the same way, what makes them so different? As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. There are 8 worlds in our solar system, but now we know that they are just a small part of the huge family of planets in the sky. It's a very important moment in the history of science to be sure that there are other systems of planets out there. In our Milky Way galaxy, which has 200 billion stars, there are probably dozens of planets. NASA sent the Kepler Space Telescope into space in 2009 on a 6-year mission to find new planets that orbit other stars. So far, they've found more than 400. Some are huge, spinning balls of gas that are 5 times as big as Jupiter. Others are large rocky worlds, many times larger than Earth. Some follow wild, erratic orbits, so close to a star that they're burning up. One thing is clear, no 2 planets are the same. Each one is unique. But most of these new worlds are very far away and hard to study. Most of what we know about how planets work comes from the 8 that orbit our sun. Our own planets come in 2 main types. There are 4 rocky planets in the inner solar system, Mercury, Venus, Earth, and Mars, and in the outer solar system, there are 4 giant gas planets, Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the other 7. When our solar system was born 4.6 billion years ago, they started to develop their own characteristics. When the sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the rocky ones closer to the sun and the gas planets farther away, came from this cloud of space debris. All of the worlds in our solar system are made of the same materials. They're made from the same cloud of gas and dust, but they formed under very different conditions. Some formed close to the sun, where it was much hotter, and some formed far away, where it was much colder. And since the conditions were so different, the planets that emerged from them are also different. At the beginning of the solar system, there was a pretty even mix of silicates, water vapor, hydrogen, lots of hydrogen, methane, and other elements. These elements in the dust cloud are like ingredients in a cake. They bake in different ways depending on how the ingredients are mixed and how hot the oven is. Just like baking a cake, you mix the ingredients, put put it in the oven, and let it bake. And things change. This is basically what happened in the solar system. Overall, a planet cooks in a slightly different way depending on how close it is to the sun. Near the sun, where it's hot, gases burn off and water boils away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the sun. As a planet moves farther away from the sun, it cooks in a different way. But what kind of planets form depends on what's in the cloud. Based on what kind of cloud a solar system forms in, it might not have any rocky planets because it didn't have enough material to make something like Earth. Instead, it might have more gas giants and no rocky planets at all. If you want planets made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the materials with a high boiling point start to condense into solids. These very small mineral grains can start to form. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If one dust molecule hits another dust molecule, they combine to form a slightly bigger dust molecule, and they keep getting bigger and bigger. This process is called accretion. As these particles get bigger, they become rocks. Then rocks slam into other rocks and form boulders. Boulders smash together to form even bigger boulders. At some point, something becomes big enough that its weight is strong enough to start pulling things toward it. So instead of just crashing into things and getting bigger that way, it actively pulls things in. At first, there were many young planets in our solar system, maybe around 100. Most of them didn't make it. If you go to the asteroid belt and look at the asteroid Vesta, you can get a good idea of how big a planet needs to be to pull itself into a sphere shape. Vesta is only 329 miles across, which isn't quite big enough to be a sphere. To become round, a growing planet needs to be at least 500 miles across. At that size, it has enough gravity to crush itself into a sphere. Anything smaller remains an irregular shape. Every time a baby planet crashes into something, it gets hotter and hotter until it starts to melt. Gravity begins to sort the heavy materials from the lighter ones. Lighter materials tend to float up and form a crust, while heavier materials, like most metals, sink down and form a much denser core at the planet's center. Finally, the young planets are starting to look like planets, but now they have to survive a time of violence and destruction, a brutal time that will decide which planets live and which die. After the Sun formed, all 8 of our planets came from the same cloud of dust and gas, but they turned out very different. There was no clear plan for how each of the new planets should form. They followed the rules of physics and chemistry, but most of what happened was just a matter of chance. About 4.5 billion years ago, our Sun was surrounded by about 100 young planets. It turned into a demolition derby, planets crashed into each other, and most were wiped out. The early history of these planets was incredibly violent, with many collisions happening in the last stages of each planet's growth. As these collisions occurred, some planetesimals started to grow at the expense of others. These objects that would eventually become planets grew larger and larger. As they got bigger, they sucked up all the smaller planetesimals around them, causing a lot of space debris to hit the surface of the protoplanets. In the end, there were only 4 rocky planets left. Because of the different events that happened to each planet in the past, they are all very different from one another. Mars is a frozen wasteland, Earth has flowing liquid water, Venus is filled with volcanoes, and Mercury is small, barren, and very hot. For example, due to a massive collision, Mercury has a very thin crust and is extremely dense. It could have been a larger planet in the past, but something hit it at an angle, stripping away the lighter crust and leaving only the dense core. Earth also experienced a massive collision during its development. Something crashed into the young Earth, tearing apart its mantle, and the debris was sent into orbit, where it eventually formed the Moon. Mars also seems to have been struck by something. The planet's crust is thinner in the north than in the south. One theory suggests that Mars' northern hemisphere was hit early in its history, blowing off much of its crust, which later built up in the southern hemisphere. There were two major effects of these collisions. First, they reduced the number of surviving baby planets, and second, they delivered additional material to the planets that survived. For instance, if a collision involved a metal-rich object, the metal would sink down to the core of the planet. If the collision involved a lighter or icy object, it would float and form part of the planet's crust. Near the Sun, there were 4 rocky planets nearing completion. They had solid cores of hot iron, surrounded by a layer of liquid iron, topped with a shell of molten rock, and finally a crust on the surface. Although all these rocky planets were made in the same way, from the same basic materials, they turned out to be very different sizes and densities. Space may look empty, but it's not. It's full of material ejected from the Sun. The Sun generates strong magnetic fields that rise in giant loops above its surface. When these loops collide, a storm of extremely hot, charged particles shoots out into space. This is known as the solar wind. Astronauts can see the effects of solar wind from space, but only when they close their eyes. When you close your eyes, sometimes you see a small flash of light, which is caused by an energetic particle passing through your head and interacting with the fluid in your eye. Astronauts see these flashes every few minutes. Solar wind could be deadly to astronauts if they were exposed to large amounts of it. During the Apollo program, there was a solar explosion between 2 moon missions that would have been fatal to astronauts if they had been there. This shows how dangerous space radiation can be. However, on Earth, the solar wind poses little threat because we are protected by an invisible magnetic field generated by the Earth's core. You can create magnetic fields from motion by converting motion energy into magnetic energy. Deep within the Earth, as the planet spins, hot liquid metal flows around the solid core, generating a magnetic field that emerges from the poles. This field deflects solar wind away from the planet, shielding the atmosphere and surface. Occasionally, solar storms disturb this field, creating auroras over the poles. Without Earth's magnetic shield, the solar wind would strip away the atmosphere and water, leaving a barren, dead planet like Mars. Mars, like Earth, formed the same way but is now cold and dry. NASA sent 2 rovers, Spirit and Opportunity, to Mars in 2004. They discovered a dry, dangerous desert with only a fraction of Earth's atmosphere but found evidence that water once existed. Mars wasn't always barren. Water once flowed beneath the surface and over the land. We see signs of water erosion, like ripples formed by flowing water. If Mars had water, it likely had a much thicker atmosphere too. Mars had volcanoes and a hot iron core, similar to Earth's. This core would have generated a magnetic field. However, because Mars is smaller than Earth, it lost heat more quickly, causing its liquid core to solidify. Once the core froze, convection stopped, the magnetic field disappeared, and solar wind stripped away the atmosphere and water, turning Mars into the cold, barren planet it is today. The rocky planets, Mars, Earth, Venus, and Mercury, all formed within 150 million miles of the Sun. But much farther out, the Sun's influence shaped a different kind of planet, the gas giants. These massive planets, Jupiter, Saturn, Uranus, and Neptune, are made mostly of gas and have no solid surfaces. Astronomers have discovered over 400 distant gas giants in other solar systems, and our solar system has 4, Jupiter, Saturn, Uranus, and Neptune. These gas giants have thick, soupy atmospheres of hydrogen, helium, and methane. Why are the outer planets made of gas while the inner ones are rocky? In the outer solar system, it's very cold, about 500 million miles from the Sun. During the solar system's formation, this region was filled with dust, gas, and frozen water. It was cold enough for snow to form, and we believe ice and snowflakes helped create the cores of the gas giants. These cores grew massive, about 10 times the size of Earth, with strong gravitational pull, which allowed them to gather thick, gaseous atmospheres. The more gravity they accumulated, the bigger they got, attracting more dust and debris. This debris also formed the many moons around these planets. For instance, Jupiter and Saturn each have more than 60 moons. The gas giants have another unique feature, rings. Saturn's rings are the most famous, but Jupiter, Uranus, and Neptune also have rings, though they are weaker and harder to detect. All 4 gas giants have rings, but Saturn's are the most visible. From a distance, Saturn's rings look like a single, flat disk. However, they are made of thousands of smaller rings, each only a few miles wide. When the Cassini probe flew by, it found that billions of pieces of ice and space debris move inside Saturn's rings at speeds of up to 50,000 miles per hour. These pieces of ice and rock collide constantly, some form small moons, while others break apart. However, none of them grow larger because Saturn's immense gravity tears them apart. Scientists are just beginning to understand how these rings formed. One theory is that a comet collided with a moon, knocking it out of orbit and bringing it closer to Saturn. Saturn's gravity then ripped the moon apart, and the debris formed the rings that orbit the planet. But the greatest mysteries of the gas giants lie deep within them, tens of thousands of miles below their clouds. This region defies natural laws. Most of the new planets we discover around distant stars are massive gas giants, so large that Jupiter seems small by comparison. However, no one knows exactly what happens inside these gas giants, whether in our solar system or in distant star systems. We know that Jupiter's thick atmosphere extends 40,000 miles deep, and we can observe bands of gas moving at high speeds, creating violent storms on its surface. But what happens beneath the storms is still unknown. NASA sent the Galileo spacecraft on a 14-year mission to Jupiter to uncover some answers. On December 7, 1995, Galileo sent a probe into Jupiter's atmosphere at a speed of 160,000 miles per hour. As the probe descended through the thick air, a parachute slowed it down. The probe observed lightning in the clouds and winds reaching 450 miles per hour. It transmitted data back to Earth for 58 minutes. What happened to the Galileo probe? It never hit anything solid, it just kept falling into Jupiter's atmosphere. As it descended, the pressure increased more and more. It recorded pressures 23 times higher than on Earth and temperatures more than 300 degrees higher than on Earth. In the deep atmosphere of a gas giant, even without a solid surface, the sheer weight of the material eventually crushes anything that falls into it. The probe was crushed after descending just 124 miles. Despite the short transmission, Galileo's probe provided scientists with a glimpse of Jupiter's interior. However, the planet's dark, hidden core remains a mystery. Like some rocky planets, gas giants also have magnetic fields. Jupiter's magnetic field is 20,000 times stronger than Earth's and so massive that it extends all the way to Saturn, more than 400 million miles away. Jupiter's magnetic field, like Earth's, shields its atmosphere from solar wind. However, it also influences its moons. For example, the volcanic moon Io, which orbits just 217,000 miles from Jupiter, ejects a ton of gas and dust into space every second. This volcanic activity intensifies due to Jupiter's magnetic field, which creates powerful belts of radiation. This makes the area around Jupiter very active. If you point a radio antenna at Jupiter, you can actually hear the interaction between the planet and its magnetic field. Jupiter and Saturn can generate auroras without the need for solar wind because they create their own magnetic fields, thanks to their massive size. These auroras show that gas planets also have magnetic fields. But how are magnetic fields created on gas planets? On Earth, they are produced by the movement of very hot liquid metal spinning around the planet's solid iron core. Gas planets likely have a similar process, but they don't have hot iron cores. Instead, they formed around frozen cores of dust and ice, so what's happening inside them remains unknown. We don't fully understand what lies deep within Jupiter's interior. It's possible Jupiter has a solid core, or it could still be in a liquid state. We may never know for sure, as no probe could survive the journey to the planet's core, which is over 44,000 miles deep. The Galileo spacecraft was destroyed before it could reach the center. Gravity and heat shape how planets evolve from their inner cores to their outer atmospheres. These are the great forces that build planets, but there is another important factor that influences a planet's development: water. While planets may seem static, they are always changing. One planet in our solar system lost its atmosphere and became a desert, while another overheated and became a hellish world. Earth, too, has undergone change, with water playing a major role in shaping its environment. When you look at Earth from space, it appears to have a lot of water. After all, we are known as the blue planet. But Earth is not as wet as it seems. Only about 0.06% of Earth's mass is water. Some water is on the surface in oceans, while some is trapped within minerals. However, compared to other planets, Earth is relatively dry. All of the rocky inner planets, including Earth, formed close to the Sun, meaning they started out dry. Any water they might have had either evaporated or was blown away by massive collisions. These early collisions were so violent that if there had been water on Earth, it would have evaporated and disappeared. So, where did Earth's water come from? The answer is likely asteroids and comets. Far from the Sun, there were many asteroids and comets that contained water. Over time, some of them crashed into Earth, delivering water that eventually formed our oceans. Without this water, life as we know it would not have been possible. What if Earth had too much water? The oceans would be much deeper, covering the continents and even mountains like Everest. The exact amount of water on Earth may be what made it possible for humans to evolve into a technological species. About 4 billion years ago, a barrage of comets and asteroids brought just the right amount of water to Earth, shaping the planet into what it is today. The same process could be happening on other planets in the universe right now, as water is abundant throughout the cosmos. The most common atom in the universe is hydrogen, and oxygen is one of the next most common, making water a common molecule. Water is everywhere in the universe, and planets are too. However, we have not yet found a planet with liquid water like Earth. So far, scientists have discovered more than 400 planets, but none have been like Earth in terms of size, mass, and chemical composition. Finding another Earth-like planet is a major goal for humanity, the holy grail of planetary exploration. Our galaxy alone has around 200 billion stars, and up to 40 billion of them may have planets. We are entering a golden age of planetary exploration, where we will begin to truly understand the diversity of planets beyond our solar system. The laws of physics and chemistry tell us how planets form, and many scientists believe it's only a matter of time before we find another planet like Earth, one with the right conditions for life. One thing is certain: there are billions of planets waiting to be discovered. The search for life beyond Earth is just beginning, but early discoveries suggest that there are many planets similar to ours. Observations from both Earth and space have confirmed thousands of planets outside our solar system, and our galaxy likely holds trillions. However, we have yet to find any evidence of life beyond Earth. Is life in the universe common and easily formed, or is it incredibly rare? These are some of the theories about extraterrestrial life. One theory suggests that life does exist elsewhere in the universe, possibly even within our own solar system. Microbial life could potentially exist on Mars or on some of the moons of Jupiter and Saturn, for example. More complex life forms, such as intelligent civilizations, could also exist on planets orbiting other stars. The Fermi Paradox. The Fermi Paradox questions why, if intelligent life is common in the universe, we haven't detected any evidence of it. Some theories suggest that intelligent civilizations tend to self-destruct, while others propose that they are too far away or have no interest in communicating with us. Ancient aliens. This theory suggests that aliens have visited Earth in the past and have influenced human history and culture. Proponents of this theory point to ancient artwork and texts as evidence of alien visitation. UFO sightings. Unidentified flying objects are often cited as evidence of alien visitation. While many sightings can be explained by natural phenomena or human-made objects, some remain unexplained and could potentially be evidence of extraterrestrial visitation. The simulation theory. This theory proposes that our entire reality is a computer simulation created by an advanced civilization. While not specifically about aliens, this theory suggests that the creators of the simulation could potentially be an extraterrestrial civilization. To start with, let's address the most basic question: do aliens exist? According to the Drake equation, developed in 1961 by astronomer Frank Drake, the probability of intelligent life existing elsewhere in the universe is high. The equation factors in the number of stars in our galaxy, the number of planets that could potentially support life, and the probability of life forming on those planets. Using these factors, the Drake equation estimates that there could be millions of intelligent civilizations in our galaxy alone. But the question remains, have we ever encountered these civilizations? Many people believe we have, and there are countless stories of alien sightings, abductions, and encounters. However, there is little concrete evidence to support these claims. Now, let's explore some of the most popular theories about what aliens might look like. The traditional image of aliens as small, green, big-eyed beings is a product of popular culture. However, it is unlikely that aliens would look anything like this. In fact, it's impossible to predict what aliens might look like, as their appearance would depend on the conditions of the planet they evolved on. For example, if an alien species evolved on a planet with high gravity, they might have shorter, stockier bodies. If they evolved on a planet with a harsh, radiation-filled environment, they might have evolved to be more resilient to radiation. It's also possible that some alien species might not even have bodies as we know them. They might exist as pure energy or as a hive mind collective. But why would aliens visit Earth? There are a few possible reasons. Some scientists speculate that aliens might be interested in our planet because of its unique location in the universe. Earth is in the Goldilocks zone, it's not too hot, not too cold, and has the right conditions for life to thrive. Aliens might be interested in studying our planet to learn more about how life can survive in these conditions. Another reason aliens might visit Earth is to make contact with us. If there are millions of intelligent civilizations in the galaxy, it's possible that some of them are trying to communicate with us. However, if this is the case, they might be communicating in ways we can't comprehend. Their methods of communication might be vastly different from ours. So, what should we do if we ever encounter aliens? Many scientists believe that we should approach any encounter with caution. We should avoid making any sudden movements or aggressive actions, as these could be misinterpreted by the aliens. Instead, we should attempt to communicate in a peaceful and non-threatening manner. If we do make contact with aliens, it could have profound implications for our understanding of the universe. It could challenge our beliefs about our place in the cosmos and force us to confront some of the big questions about life, the universe, and everything. Now that we've explored some of the theories and possibilities of alien life, let's consider the idea of the Fermi paradox. This paradox asks the question, if there are so many intelligent civilizations out there, why haven't we seen any evidence of them? Why haven't we detected any signals or observed any spacecraft from other worlds? One possibility is that advanced civilizations tend to self-destruct. With technology comes the potential for destruction, whether through environmental damage, war, or some other catastrophe. It's possible that many intelligent civilizations reach a point where they are unable to sustain themselves and ultimately fail. Another possibility is that intelligent civilizations have no desire to make contact with us. Perhaps they are simply not interested in Earth or in communicating with other species, or perhaps they are too far away to detect our signals and we are too primitive to detect theirs. Regardless of the reasons, the Fermi paradox remains a mystery and a subject of much speculation. But let's turn our attention to the possibility of life in our own solar system. While we haven't found any evidence of intelligent life, there are some promising signs that microbial life might exist on other planets or moons. For example, NASA's Mars rover has detected methane on the planet's surface, which could be a sign of microbial life. Scientists have also found evidence of subsurface oceans on some of Jupiter's and Saturn's moons, which could potentially support life. If we do find evidence of microbial life in our own solar system, it would be a major discovery and could have significant implications for our understanding of life in the universe. Let's consider the potential implications of discovering intelligent life. If we were to make contact with an alien civilization, it could have profound impacts on our society and our understanding of the universe. For one, it could challenge our existing beliefs and worldviews. We might need to reevaluate our ideas about our place in the cosmos, our religious and philosophical beliefs, and our understanding of the origins of life. It could also raise questions about the ethics of interacting with other intelligent species and the responsibilities that come with such interactions. Another potential impact is on our technology and scientific progress. If we were to encounter a more advanced civilization, we could learn from their technology and knowledge, potentially accelerating our own progress. On the other hand, it could also pose a threat if the aliens have hostile intentions toward us. It's difficult to say for certain whether aliens, if they exist, would be dangerous to us. We have no concrete evidence of intelligent extraterrestrial life, so any speculation about their intentions or behaviors is purely hypothetical. Some people argue that aliens could be dangerous if they are more technologically advanced than us and have the ability to conquer or destroy us. Others point out that any civilization advanced enough to travel through space would likely have a more sophisticated understanding of the universe and may be more peaceful and cooperative. It's also possible that aliens could be indifferent to us, simply observing us from a distance without any intention to interact with us at all. Overall, while it's fun to speculate about the potential dangers of alien life, the truth is that we simply don't know enough to make any definitive conclusions about their intentions or behaviors. The search for extraterrestrial life should be approached with an open mind and a healthy dose of curiosity rather than fear or paranoia. Regardless of the potential impacts, the search for intelligent life continues. We are constantly developing new technology and refining our techniques to search for signals and evidence of other civilizations. And while the chances of finding intelligent life may be slim, the pursuit of knowledge and discovery is a worthy endeavor in and of itself.